Antibiotics. Antibiotics are medicines that fight infections caused by bacteria in humans and animals by either killing the bacteria or making it difficult for the bacteria to grow and multiply. We can discuss some structural activity relationship of antibiotics. Structure activity relationship of chloramphenicol. A large number of analogues of chloramphenicol have been prepared, but the antibacterial activity of the parent antibiotic is found to be more effective than other analogues. If the phenyl ring of the chloramphenicol is replaced by a heterocyclic ring, then the resulting antibiotic is found to be less effective than chloramphenicol. The nitro group in the phenyl ring of chloramphenicol is replaced by cyanide group, amide group, primary amine group, hydroxyl and secondary amine group, and their physiological activity is tested. It has been found out that the compound with these modifications show antibacterial activity. Dichloroacetyl group of chloramphenicol is very important for its antibacterial activity. The dibromoacetyl group has only 80% of bacterial activity. Chloramphenicol palmitate oral suspension is tasteless and is used for pediatric use. Any alteration in the nature of the side chain of chloramphenicol results in its deactivation. The propane diol moiety of the antibiotic molecule is essential for its antibacterial activity. The hydroxamic acid analog of chloramphenicol lacks antibacterial activity. The bulky substituents reduce antibacterial activity. Derivatives of chloramphenicol containing a wide range of para-substituents are physiologically active. Chloramphenicol sodium succinate has a high aqueous solubility in comparison to chloramphenicol base, hence it is used for parenteral chloramphenicol therapy. Any structural change that affects the functional character of the hydroxyl group on carbon 3 atom or altered the length of propane residue results in deactivation of the drug. Alteration in the aliphatic moiety of the molecule of chloramphenicol leads to diminished loss of activity. Any alteration in the aromatic moiety do not affect its activity. Structure activity relationship of streptomycin. The antibiotic activity of streptomycin largely depends on the hydrogen ion concentration of the medium and its composition. The efficiency of streptomycin activity decreases in an acid medium, while its biological activity is maximum in an alkaline medium. Catalytic hydration of streptomycin gives dihydrostreptomycin, which shows same biological activity as that of streptomycin. Dihydrostreptomycin is more stable than streptomycin. If streptomycin is treated with carbonyl reagents, it reacts with its aldehyde groups, resulting in complete loss of activity. The reduction of the aldehyde group in streptomycin to a primary alcohol group in dihydrostreptomycin does not abolish antibiotic activity of the dihydrostreptomycin. The presence of D-mannose sugar unit in streptomycin makes the drug less active than streptomycin. It has been found out that streptidine has low antibiotic properties. Introduction of cysteine molecule in streptomycin results in its deactivation. Structure-activity relationship of penicillin G. An intact beta-lactam and thiazolidine fused ring system was believed to be essential for its activity. Through recent development indicates that certain modifications in the thiazolidine ring retains its biological activity. The parent compound phenylpenicillin is less active than benzyl penicillin. It has been found out that the introduction of substituents in the ortho position reduces its physiological activity due to steric hindrance. The first compound produced commercially was methicillin with methoxy substituents followed by oxacillin, chloroxacillin, naproxen, etc. These compounds are not active against gram-negative organisms, although some of them inhibit a number of gram-negative lactamases. Any substituents on the carbon atom of the hydrophilic side chain of the benzyl penicillin with an amino or carboxyl group increase its activity. The esters of penicillin antibiotics are not bacteriostatic in vitro but have considerable activity in the living animal. The benzyl ester of benzyl penicillin is much more active than its parent compound. The decarboxylation of the penicillins leads to complete loss of its bacteriostatic activity. It has been found out that activity of 6-aminopenicillin acid, which is the fundamental nucleus of all penicillins, is 2000 times lower than that of benzyl penicillin. The para-hydroxybenzyl penicillin has been coupled with a number of diazonium salts in neutral solution to form azopenicillins, which allows the same activity as that of natural penicillins. Structure-activity relationship of tetracycline. The structure-activity relationship amongst the various members of the tetracycline family has been studied extensively. The high level of antimicrobial activity of tetracycline established earlier revealed that the substituents on the carbon 5 and carbon 7 were not an essential requirement. The activity of 6-dimethyl tetracycline and D-methylcycline has established that the methyl function at carbon 6 may be replaced by hydrogen. The activity of deoxycycline and 6-deoxy-6-dimethyl tetracycline shows that the presence of hydroxyl moiety at carbon 6 is not essential either. The 6-deoxy-6-dimethyl tetracycline and their corresponding mercaptan adducts possess typical characteristics tetracycline activity and illustrate further the level of modification feasible at carbon 6 with the possible retention of biological activity. It is, however, interesting to observe that the subsequent removal of the 4-dimethylamino function affords a loss of about 75% of the antibiotic effect of the parent tetracyclines. X-ray diffraction studies further reveal that the 4-dimethylamino function is placed in a trans orientation rather than the cis form as inferred earlier by chemical investigations. A further establishes the presence of a conjugated system existing in the structures of tetracycline from carbon 10 through carbon 12. Structure activity relationship of ciprofloxacin. The amino group is toxic. Successive alkylation of the amino group decreases its toxicity. In general, the acylation of amino group decreases the physiological activity. The replacement of hydrogen atoms by alkyl groups diminished their biological activity. The fluorine group is comparatively much less physiologically active than the corresponding other halogens. The less activity of fluorinated compounds may be due to their stability.